In this video, I would like to prove for you that a function which is continuous on a compact set has a compact image. So let's sketch a picture of what's going on, and to our sketch, I will add the proof technique. Suppose that K is a compact subset of the metric space M, so K is compact, F is continuous, and F of K is just the image, potentially in a different metric space. I'll just call it capital N. What we want to say is that if this is compact and this is continuous, then this is compact. I'm actually going to prove this for you two different ways. It's not necessary to do two proofs, but I think it's illustrative in this case. So we are going to prove that this set is compact by first showing that it's sequentially compact. So I will appeal to Bolzano-Weierstrass and say that if we can show it's sequentially compact, then that's enough. That would verify that this is compact. Then for the second proof, I will prove that any open cover of f of k must yield a finite subcover, so we will prove that f of k satisfies the true definition of compactness. The reason why I want to do both proofs is because they follow such a similar flow of ideas that I think seeing them together helps you recognize how to prove statements like this. So in fact, when we look at, say, similar statements in the next video about path connectivity, it will follow the same train of thought. So maybe you'll be able to anticipate how to proceed with that proof before I even do it. Okay, our first proof is going to involve sequences. Let me sketch the idea. We want to show that every sequence in f of k has a subsequence which converges to a limit which is in f of k. That means that the first line of our proof must start with a random sequence in f of k. Sometimes I see students start with a sequence in K, but that's not really the right way to begin a direct proof that this is sequentially compact. A direct proof should really follow the statement of the definition, and the definition of sequential compactness for f of k is every sequence in f of k yields a subsequence which converges to a limit in f of k. So you really want your first sentence in your proof to be let x sub n be an arbitrary sequence in f of k. You don't want it to feel designed, which is how it might feel if it's being inherited from K. So start with a random sequence here. Okay, there, I've said it. All right, so imagine we have a random sequence in f of k. What we're going to do is pull back to K through the idea of preimage. Now, f is not necessarily one-to-one, which means that when I look at this sequence point right here, and I pull it back, maybe 10 inputs from K get mapped there. You just want to pick one. So I'll clarify that in the proof, but I just want you to anticipate that. So I'll say for this point, pick this input, and we'll get like a sequence of inputs that maps exactly to our sequence of outputs over here. By pulling back to K, we create a sequence in a compact set. Since a compact set is also sequentially compact, then we can say, hey, look, there's a subsequence which converges to a limit in K. We will then map that back to f of k, so pull back, then come back over here and say, hey, look, that's producing a sequence here, a subsequence of our original sequence. And then we'll use the sequential description of continuity to say, hey, that's got to converge, and it's got to converge to something in f of k. So this is the idea of the first proof that we will do, that if we create a sequence here, we can pull it back, do some stuff here, send it back forwards to create a subsequence which will converge in the set. Let me now let you kind of digest that. You can start to think through the ideas of the proof, then I will write up the proof for you. Then we will look at the open covers approach. All right, let's write down the proof now, and it's going to follow the thought process that we just went through. Let y sub n be a sequence in f of k. I don't want to be more specific than that, because the definition of sequential compactness says any sequence in f of k yields a subsequence which converges in f of k. So I want to be like very vague here. For each index n, pull back. So for each index, choose an input from K. we'll call it x sub n, to map to y sub n. So choose a term x sub n in K so that y sub n is f of x sub n. I'm not going to write it down, but this choice is not necessarily unique. As I mentioned, there may be 10 inputs which get mapped to a given output. Just pick one of them. Okay, so that's why I put A here. So choose a term so that that term gets mapped to y sub n. Now x sub n is a sequence in K. The sequence in K, and let me mention here that since K is compact, K is sequentially compact. And since K is compact, K is sequentially compact. And that is the famous result from Bolzano-Weierstrass. All right, let me pause here. In our picture, we're now back on the left. All right, take a moment to see if you can write down maybe the next few sentences. If you're feeling really good about the thought process with the proof, you could try to go all the way. All right, our next step is to recognize that since x sub n is a sequence in a sequentially compact set, there is a subsequence which will converge in K. So thus, I'm going to write there exists x sub n sub K converging to x naught in K. All right, so abbreviated notation here, but there exists a subsequence which converges to a limit that lives in K. It's not like an accumulation point outside of K. We know that the limit is in K. All right, at this point, we've done a lot. One thing we have not done is ever use the continuity of F. The fact that I can pull back to inputs, that has nothing to do with the fact that F is continuous. That's just because F is a function from K to F of K. Now we use continuity here. So by the sequential characterization of continuity, if this is happening in the domain, f of x sub n K is going to converge to f of x naught in the codomain, so in the target space. So by the sequential characterization of continuity, markers. It's nice here, it's going to go right under this. So f sub x sub n sub K converges to f of x naught, which by construction is in f of K. So if x naught is in K, this is in f of K. At this point, we are basically done. This is the subsequence that we need, but let's translate back to the original notation so that the reader really makes the connection. So y sub n sub K is this, right? So therefore, let's say y sub n sub K, which is exactly what we mean when we say f of x sub n sub K, is a subsequence of y sub n Sorry, I'm being a little bit casual here with my sequence notation, but this is a sequence, this is a sequence. I'll just leave it. Which converges in f of x k, f of k. Okay, is a subsequence of this which converges in f of k. So f of k is sequentially compact, and that is enough by Bolzano-Weierstrass. You can write that. I'll just go ahead and end my proof there, in part because my marker is getting squeaky. Okay, to recap, we needed to start with an arbitrary sequence in f of k. We wanted to show that from that sequence, we can produce a subsequence which converges in f of k. So the limit does not live outside of the set. That is exactly what we have now done. So we have done a direct proof that f of k is sequentially compact. And what I want you to notice is how much this direct proof mirrors the definition of sequential compactness. So we started and ended with the beginning and ends of the definition of sequential compactness. What did we do along the way? Well, with our sequence in the target space, we pulled back to the domain because that's where we knew something to be true. We knew K to be a compact set, therefore sequentially compact. So from the sequence that we generated in the domain, we could pass to a subsequence, which we knew converged in the domain, and then continuity. Always with this kind of statement, look for where the hypotheses are being used. So it's here and it's here. Okay. So by the continuity of our function f, a convergent sequence in the domain turns into a convergent sequence in the codomain, and that's what gives us what we needed. Okay, so our hypotheses, which I've just underlined where they're used in the proof, were that the domain is compact and the function is continuous. All right, let's go back to our diagram, and I will illustrate how much the open covers approach is going to mirror this thought process, and then we will do that proof as well. Returning back to our diagramming step, again, we want to prove that f of k is compact, but this time by using open covers. Just like before, it's going to be a direct proof that f of k satisfies the definition of compactness, which means that every open cover of f of k must yield a finite subcover. Therefore, the first step in our proof is going to be to imagine that we have a random open cover of f of k, one that we did not design, one that we're just being given. So imagine this is some random open cover of f of k, probably with infinitely many open sets. Otherwise, it wouldn't be very interesting. All right, we have an open cover of f of k. What we're going to do is pull these back to k and imagine, kind of have to do some justification here, that each of these open sets is going to map back to a kind of open set. And what that will create is an open cover of k, which we know by hypothesis to already be compact. Therefore, since we will then be looking at an open cover of a compact set, we can say, well, here's a finite subcover. And then we send it back with f and say, okay, look, that means that we have a finite subcover from our original open cover. Okay, the picture is like super messy now, I'm sorry, but it's the same thought process that we had with sequences. Start here, pull back to the domain where you know that compactness is already true, do what you're allowed to do with compactness in the domain, and then map back to the codomain. Along the way, continuity will give us something important. All right, so take a moment to go ahead and write the first sentence of the proof based on this now quite terrible looking picture. To say that f of k meets the definition of compactness is to say that any open cover of f of k yields a finite subcover. Since our proof is going to be direct, it's going to mirror the flow of that definition, which means my beginning sentence is going to be, let such and such be an open cover of f of k with no further specification. And then my ending sentence will be something like, and therefore it yields a finite subcover. Okay, so just like with sequential compactness, the proof we did a moment ago, we are going to start in f of k. We have to start there. The proof, let, it's just a random family of open sets be an open cover of f of k. Okay, so here the idea is that each u sub lambda is an open set. I don't know what this family looks like, so that's why I'm indexing with lambda rather than n. I don't even know if it's a countable collection of open sets. It could be uncountable. So this is just an arbitrary family of open sets, and together their union covers f of k. So every element in f of k is inside one of these open sets. We need to pull back to the domain. And in order to do that, I'm going to bring in the topological characterization of continuity. So this is where continuity is going to come in. As f is continuous, for each index lambda, there exists an open set O sub lambda And let me add here that this open set is in the metric space that is the domain of f, or the domain of f is part of the metric space M. And over here, This is in the target metric space N. Okay, continuing the sentence. As f is continuous, for each lambda, there exists an open set back in the original metric space M, so that the preimage of u sub lambda can be written as the intersection of O lambda and A. This is the topological characterization of continuity, which says that the preimage of open sets is open relative to the domain. So open relative to the domain means it can be written as an intersection of an open set and the domain. Then I want to point out here that this intersection is a subset of O sub lambda. I think that just helps to see the next step. All right, I claim that the family of O sub lambdas is now an open cover of K. It might feel obvious, but I would like for us to do this proof very in full detail. So I'm going to prove that, okay, this is already open. I'm going to prove that this covers K. Okay, that is open is given by the topological characterization of continuity. So now let's verify that K is being covered. For any x in K, f of x lives in some u sub lambda. So there exists a lambda naught so that f of x is an element of u sub lambda naught. Therefore, x is in the preimage of that, which is a subset of O lambda naught. So x is in the preimage of this set, which, like appealing to the line above, means x is in O lambda naught. I'm trying to use matching subscripts. Okay, so U lambda naught goes with O lambda naught. All right, so for any x in K, I can now identify an O lambda naught that that is an open set that x can be found inside of. Okay, so for each lambda corresponding to this family of open sets covering f of K, we are going to grab O sub lambda through this kind of action of pulling back. And now this family of O sub lambda is a cover of K. So then this family O sub lambda is an open cover of K. Open here. All right, just like before, let's pause, take a moment to digest this, and then see how far you can take the proof. Before I let you go, I just realized I don't like saying then there. I want to say thus to really say that this follows. So, thus, okay, it's an implication. All right, now pause. Continuing now, since K is compact, this open cover of K must yield a finite subcover. So since K is compact, I'm going to use shorthand here or else I will run out of space. So since K is compact, there exists a finite subcover. That's what that stands for. There exists a finite subcover. How I'm going to write this down is, lambda could have been an uncountable set. So maybe for every real number, I had a u sub lambda. We are now passing to a finite subcollection of this family, which means that I can index them in a more countable looking way, in fact, a finite way. So let me call these O sub lambda 1, O sub lambda 2, all the way through O sub lambda capital N. Okay, so maybe there are 50 of these, and together, this is all we need to cover the compact set K. We now want to show that the original sets that these correspond to. So each of these was created in response to one of these open sets. If we go back to this family now, I want to say that U lambda 1, U lambda 2, all the way through U lambda n, the partners of these back in the codomain, is a finite subcover of the original set that we were analyzing, f of K. To do that, it's going to follow the same thought process as here. For any y in f of K, choose an input x in K so that y equals f of x. Maybe you don't have a choice. Maybe there's just one input, or maybe there are 10, but grab an input that gets sent to y. Then x must live in, say, O lambda j, where that's maybe here. X is in O lambda j, where j is some number between 1 and capital N. Consequently, we are almost done. Consequently, y is in the image of O lambda j intersect A to keep us in the domain. But that is literally how we pass from the domain back to the original open sets U. Sorry, I didn't say that very well, but this is literally what it means to get sent to U lambda j. Therefore, all of the original sets that correspond to this finite group forms a finite subcover of f of k. Okay, let's see if I can squeeze this here. Thus, U lambda 1, U lambda 2, all the way through U lambda n is a finite subcover of f of k. And we have what we need now, so I will wrap it up there, but you might want to say, therefore, f of k is compact. All right, let me have you read through this, finish writing it, and then we will come through and summarize. All right, let's talk through this proof. It mirrors the proof that we did first, that f of k is sequentially compact, but I think it's a little harder for students to follow this one compared to the approach with sequences. That's often the case with open covers. That's why I like to teach sequential compactness before teaching compactness. But again, it follows the same train of thought. So what we did was we started with an arbitrary open cover of f of k. I think passing back to the O lambda is the hardest part for students to follow. There's no prescriptive form for what these look like. What we're saying is for each one of these, so go through every single one of these, it could be an uncountable collection, but for each one, there should be an O sub lambda back in the domain or back in the original metric space so that the preimage of U lambda can be written as the intersection of O lambda and the domain. That is where we used the continuity of F. So this part, this is really the only step on the entire proof that appeals to the continuity of F. Okay, so because F is continuous, we can do this. So for each one of these, there is an O sub lambda. Again, the lack of like prescriptive form, I think, is what sometimes students struggle with, but like we can just pull these back. Okay, then we have all these O sub lambda. Turns out with this quick little verification that that forms an open cover of K. K is compact, so here's our other hypothesis, allowing us to pass to a finite subcover. And then it's like, okay, each one of these was created in response to a U sub lambda, so an original open set. So since each one of these was created in response to one of the U lambda, let's go back to those original ones. So each one of these should go back to a U sub lambda, and that's what we have here. So O lambda 1 is whatever was created in response to the set U lambda 1. So this is a finite subcollection of what we started with. It covers f of k, verifying that f of k is compact. We started with a random open cover, and we ended with a finite subcover. So again, our direct proof mirrors the flow of the definition of compactness. All right, thank you for your attention. I hope that you did watch through both proofs. You never need to prove something in math twice, but I think in this case, these proofs look really nice together side by side. They follow the same kind of logical flow of ideas. And if you understood them, you'll realize that each step is exactly what must come next, meaning that if you're going to prove that f of k is sequentially compact or compact directly, you pretty much have to follow this train of thought. So I like them read together. In the next video, or one of the next videos, we will prove that if f is continuous and k is path connected, then f of k is path connected. And it will follow a very similar train of thought. In fact, if you have the definition of path connectedness handy, you might see if you could write down a proof now that you're in the spirit of this, because again, the flow of the ideas is going to be exactly like what we did in this lecture. All right, I'll wrap it up here. Thank you for your attention.